Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the revision of deflection of the beams. What is the deflection of beams, and when will it occur? Those deflections. Deflections will be occurred when the load is applied on the beam. Suppose if you consider a simply supported beam, applied the load W, then the beam will be deformed, bent like that. This is known as the deflection. So the deflection can be measured and can be observed directly by using various methods. Now here, whenever we are going to design any beam or structure, we need to consider the two parameters. The strength and stiffness are required. The strength criteria can be done by doing the shear force and bending moment calculations. That means here, the shear force, variation of the shear force across the section of the beam, and also variation of the bending moment across the section of the beam. So the strength means here the section modulus represents the strength of a beam. So the strength, how it is represents, the more becomes the moment of resistance, that means the more strength. So moment of resistance is proportional to the section modulus. That's why the section modulus represents the strength of a beam. Another one is that stiffness. The stiffness of a beam can be calculated based on the deflections. If the deflection is small, the stiffness is high. If the deflection is low, that means the stiffness is, if the deflection is very high, that means the stiffness is low. So stiffness K equal to load per deflection. So here the deflection inversely proportional to the deflection. If the deflection, the value of the deflection is maximum, then the stiffness is low, minimum. So for the same load, for different loads, here the point is that, so the stiffness can be calculated by using the deflection of the beam. So deflections are, values of the deflection are highly important in order to measure the property of the material, that is the stiffness. When the load is applied, on the beam, the beam will be deflected or bent in this direction, like a curve. This curve is known as the elastic curve. So let us find out the governing differential equation of a beam. Now here, when the load is applied, after applying the load, the elastic curve, consider the elastic curve's element, that is a PQ. If you draw the tangents, then, and those two tangents, if you draw a normals, the normals of these two tangents will be intersected at point O. The radius of curvature, this is the R, at a certain radius, that is known as the radius of curvature. The elemental PQ, the distance, that is length, is the ds. And there is a slope of inclination. So the slope is denoted by d theta. Suppose it is the ds and it is d theta, and the horizontal distance is dx. The vertical deflection is dy. So at this point P and Q, the slope is d theta and the deflection is dy for a span of dx. Dx is the horizontal distance. That horizontal distance represents the span of the beam, for the elemental span of the beam. The slope here, the ds, is the curve which is passing through that. Now this is the elastic curve. The elastic curve length is the ds, and for a span of dx, and the deflection is dy. From this, two things we can calculate. One is tan d theta equal to dy by dx. Tan d theta equal to dy by dx. When d theta is tan d theta equal to d theta, when theta is the small, that means d theta equal to dy by dx. This dy by dx is known as the slope. Now here, in relation, not to find out the relation between d theta, r and ds, that means the ds equal to r d theta. So ds by d theta or d theta by ds, that equal to 1 by r. So here point is that from this right angle triangle, that is a ds, that is the hypotenuse, where is dx horizontal adjacent side, dy is the vertical. Okay. Now, how to, here dy and dx, we calculate the ds. Tan d theta equal to dy by dx. By differentiating this equation, we'll get it. What is the word? That is secant square d theta. Let us see here. This is what theta or d theta we consider. The d theta are equal to, that is known as the elemental angle. That is also known as the theta slope. Then now here, tan theta equal to dy by dx. If you differentiate with respect to theta, that is secant square theta d theta by dx equal to d square y by dx square. This secant square theta, what is the d theta here? D theta equal to r, that is a ds equal to r d theta. ds equal to r times d theta. Now d theta equal to ds by r. Substitute in the place of d theta, ds by r. Here is 1 by dx, d square y by dx square. Now, another relation also, there is, if in terms of, this is ds theta dx and dy. What is the secant theta? The secant theta equal to ds by dx. Substitute in the place of ds by dx term, the secant theta, secant square theta times the secant theta, that is secant cube theta by r, that equal to d square y by dx square. Now we are going to convert the secant cube theta in terms of tan theta. How to make it here? The secant cube theta we are going to write as, that is secant theta whole cube. What is secant theta? 1 plus tan square theta and the square root cube. That is 1 plus tan square theta power 1 by 2 and power 3. That is known as, this is the term 1 plus tan square theta power 3 by 2. This is the secant cube theta. In the place of the secant cube theta, substitute 1 plus tan square theta power 3 by 2. This term. Now d square y by dx square equal to 1 plus tan square theta power 3 by 2 by r. Now when tan theta, the angle is very small, consider as a 1, then 1 power, that is 1 becomes, this equation is transformed to d square by dx square equal to 1 by r. D square by dx square equal to 1 by r. How we got this m by ei? Consider the equation of pure bending equation, that is m by I equal to e by r, that equal to sigma by y. Now from these two relations, m over ei equal to 1 by r. Now we already know d square y by dx square equal to 1 by r. Equate these two, then it becomes d square by dx square equal to 1 by r, that 1 by r equal to m by ei. Now take the terms, these two terms. Now d square by dx square equal to d square y by dx square equal to m by ei. This is the ei times d square y by dx square equal to m. This is the equation, the governing differential equation of bending of the beam. This is the governing differential equation of the beam. From this equation, or the bending moment at any section of the beam. This is the governing equation, the bending moment equation. This is a second order differential equation. Now, what is ei? What is the significance of ei? The ei meaning is that the ei means the product of modulus of elasticity times area moment of inertia. This ei is known as the flexural rigidity. It is the index of the bending strength. That is the flexural rigidity. Flexural rigidity. Ei known as the flexural rigidity. So, this flexural bending moment is proportional to the flexural rigidity. That means here, it indicates the bending strength, index of bending strength. of the beam is known as the flexural rigidity. Now that's what here mentioned, index of the bending strength of an element called as flexural rigidity. Why it is the moment sustained by an element is of the beam is proportional to EI. That is EI d square y by dx square equal to m, or m is proportional to EI. So EI indicates the index of the bending element or bending strength or flexural strength of the element. Now, there are some important relations, important equations to understand what is the slope, what is the deflection, what is the moment, bending moment, from that bending moment, how the shear force, from the shear force, how the intensity of the loading, that is known as uniformly distributed load, calculation can be known. Now, from these equations, we have deflection y. Differentiate deflection with respect to the span, that is dy by dx, is known as the slope. Now, multiply this slope with EI flexural rigidity and differentiate one more time of dy by dx. That means EI times d square y by dx square, that is known as the moment. Now the shear force comes. Shear force will be again dm by dx. Differentiate moment with respect to x gives the shear force, that is dm by dx, that equal to EI times d cube y by dx cube. Again differentiate differentiate the shear force df by dx, that gives intensity of the loading, that is the load intensity, that is w equal to df by dx, that equal to EI times d power 4 y by dx power 4. So these are all having certain important interlinking, okay, relations are there. If you know the deflection, from that slope can be calculated. If you know the slope and known the modulus of velocity and second moment of area, moment can be calculated. Differentiating the moment, shear force, from the shear force, differentiating the shear force equation, we'll get the intensity of the loading. So how much load is being acted from the event or from the value of the deflection. Now that means, what is the significance on these relations? The deflection comes from, if it is UDL, from intensity of the loading. It is a link between, these are all the equations are having connection, relation between the load intensity of the load intensity, suppose if it is uniformly distributed load, and the effect is output is the deflection. So in between the intensity of the loading and the deflection, there are various parameters are there. What are they? The slope will come into the picture. First, from that, because of this UDL, because of the intensity of the load, what will happen? It causes the shear force and bending moment in the section of the beam. From the shear force and bending moment causes the slope and the deflections. That is the meaning of these relations. The input is the load. Suppose if we consider the load, not only load intensity, if we multiply the load intensity per length span, load intensity with the span of the beam, that gives the weight or concentrated load. That is another equation. So if we consider the equation, that is the load, the concentrated load, because of the concentrated load leads to shear force and bending moment variations inside the beam. That causes to deflect that causes to lead the slope. The slope means inclination of the curve takes place. That a slope meaning output is the finally various different slopes at different points joining that curve leads to deflections. That's what a deflection is all about. That is one side of explanation. The another side of explanation is that if you integrate this moment equation, the moment equation, one time if you integrate, that means EI times dy by dx equal to integral m dx plus c1. That means dy by dx is nothing but a slope. That means slope will be occurred from this equation. If we integrate the slope dy by dx, that means y will come out. That y is known as the deflection. So we need here, in order to calculate the slope and deflections, the main thing is that this equation is important. That is a variation of the bending moment at any section of the beam. That equal to EI times d square y by dx square. Alright. That is the what? That is required for this. That is EI times d square y by dx square is required. Now, that's why we are going to consider this equation and equate the moment of the section of the beam. Then integrating once gives the slope, integrating the slope equation gives the deflection. That's why these two things, these three are important for our calculation purpose. So, now what are the various methods are involved in calculating the deflection of the beam? There are various methods are there. First method is the double integration method, and second method is Macaulay's method, and the third method is moment area method, and fourth one is conjugate beam method. These are the various methods, or these are the four methods are useful to calculate the slope and deflections of the beams. Now, there are certain advantages in double integration method and certain disadvantages are there. The advantage of double integration method is that it is very easy for calculating the slope and deflection of your point loads, single point load or single concentrated load on your beam. And the Macaulay's method is highly useful for multi-point loads or multi-concentrated loads and also uniformly distributed loads method. In double integration method, we have to write for various deflection, at a deflection of various sections, we have to write the number of bending moment equations. Whereas in the case of Macaulay's method, we will write only single equation. That's why it is the method of singularity function. That's called Macaulay's method. Now, that's why this Macaulay's method is highly useful for both multiple point loads and also uniformly distributed loads. So, this Macaulay's method is simple and also various types of loads we can use this Macaulay's method. Coming to moment area method, in the case of moment area method, we need two parameters. One is the area of a bending moment diagram, another one is bar x, that means the centroidal distance of that bending moment diagram. So, this is a moment area method. If we know those two things, those two parameters, we can calculate directly the slope and deflections. Now, but what is the disadvantage of this moment area method? Suppose if UDL is there, the bending moment diagram becomes quadratic curve, that is a parabolic, but there is a complexity. For various types of, if the bending moment diagram is not in the form of rectangles and squares, then it is complicated. Moment area method is more complicated. That's why we require for moment area method, the loads are acting such a way that the bending moment curve, the BMD curve becomes in the shape of triangles, combination of triangles and rectangles. So to calculate the area of bending moment diagram, that's why it is known as moment area method. So moment area method, another name is also known as Morse method. There are two theorems are there. Morse theorem 1, Morse theorem 2. Morse theorem 1 defines Morse theorem 1. Theorem 1 defines the slope. Morse theorem 2 gives the deflection. So there are two theorems, theorem 1 and theorem 2, slope and deflections. That is moment area method. The final conjugate method is the method of actually modified moment area method. We'll see it. Now we are going to discuss in this session, even though revision, we are going to revise it. What is the double integration method for various types of beams? Now let me explain a glimpse of double integration method. Okay, in the case of double integration method, we'll consider the moment equation, that is m equal to ei times d square y by dx square. Now, what is the methodology for this? In the case of double integration method, we know that ei times d square y by dx square equal to m. If you integrate ei times dy by dx equal to integral m dx plus c1. This is the slope equation, provided constant of integration c1 is known. Next, if you integrate the slope equation, ei times y equal to double integral of m dx, m dx plus c1x plus c2. This c1, c2 is known as constant of integrations. These constant of integrations are calculated by using boundary conditions. How many boundary conditions? 2 boundary conditions. The first boundary condition C1 should be related to the relation between the span of the beam and the slope. The second boundary condition C2 is related to deflection, the span x, and also deflection y, x and y related. Whereas for first boundary condition, it should be related x and theta divided by dx related. So, where there is another, in that we'll discuss more double integration methodology. This constant of integration, suppose if we consider the simply supported beam having 2 reactions. Here is the point load. When the point load acts on the beam, the deflection will be maximum in the center, where the center is the midspan acting. The load acts in the midspan. So the deflection is maximum in the midspan. Why? What is the slope here? The slope becomes 0. That means dy by dx equal to 0. Suppose you consider the point A, consider point B. At the supports, what is theta A? The theta A will be their value. What about deflection? Deflection y equal to 0. At support B, theta B value, slope will be maximum. But what is the deflection at B? It is a fixed support. Deflection is 0. So these two equations, that means at x equal to 0, consider a section distance x from here. At a distance of x equal to 0 and ya equal to 0, that condition, boundary condition, is related to deflection. And x equal to 0, at x equal to L by 2 or x equal to L by 2, what is the dy by dx? 0. So that is related to the slope condition. So in that manner, we are going to calculate the slope and deflections by using double integration method. Let us begin with the case 1 of a double integration method. And the case 1 is that here the cantilever beam is subjected to a point load W. The span of the beam is the L at a distance x. Fixed point, fixed support at A, and it is free at B. The load is acted W at the free. So for this, how to calculate the deflection and the slope? The slope means dy by dx at point B, that is means theta B and yb. What is the deflection at B and the slope at B, point B? Point B means here where the load is acting, and also where the load is acting at the free end. Let's begin at a distance of x. At this x, what is now here the origin of distance x is the fixed support. A is the origin point. From that origin point, we measure the distance x. We want the deflection at this point. That means L minus x. Now that's why the bending moment at a section x, that is minus w times L minus x, that equal to the governing equation, bending moment equation, that is I times d square y by dx square. Now if we integrate this equation once, that means I times dy by dx equal to minus w times Lx minus x square by 2 plus c1. This c1 is the constant of integration related to the slope, and the length of the beam. Now the slope at x equal to 0, what is it? dy by dx. That is dy by dx is considered 0. Then it becomes a c1 equal to 0. Why it is 0 slope here there? Because it is the what type of beam? It is the cantilever beam. X we consider from fixed support. Here x equal to 0. What is here at fixed support? A deflection, that is the slope is 0. It is a fixed support. Alright. That's why C1 value 0. Substitute this C1 value back in the equation. That equation gives EI times dy by dx equal to minus W times Lx minus x square by 2. Then from that dy by dx equal to minus W by 2EI times 2Lx minus x square. This is the equation. Alright. This equation gives the slope at a distance of x. Now we want a deflection. Now deflection means where is the equation? Now integrate this slope equation once, that EI times y equal to minus W times Lx square by 2 minus x cube by 6 plus C2. This C2 is the constant of integration that is related to deflection versus the span. X equal to 0 and y equal to 0. So that means at fixed support, both slope equal to 0 and deflection equal to 0 at fixed support theta A. That's what meaning here. Now after substituting these two conditions in the above equation, then what happens? C2 becomes 0. Substitute back in the C2, that equation gives EI times y equal to minus W times Lx square by 2 minus x cube by 6. Now deflection y equal to W by EI minus W by EI, make 2 and 6, LCM is 6, it becomes 3Lx square minus x cube. This equation gives the deflection. Now at a free end, now we want at a free end, what is the deflection, slope and deflection? At x equal to L, what is the slope and deflection? At x equal to L, substitute in that here, x equal to L, that means 3L cube minus L cube. That's 2L cube, 2 cancels is 6 3 times, minus WL cube by 3EI. That is WL cube by 3EI. Now, at x equal to L, substitute in this x equal to L in the slope equation. That is 2L square minus L square, that is minus negative of WL square by 2EI. If we want a slope and deflection x equal to L by 2. Substitute in this formula x equal to L by 2 in the deflection value, then we'll get it at a distance of L by 2. And substitute L by 2, x equal to L by 2 in the slope equation, we'll get the slope at a distance of x equal to L by 2. Thus, we can calculate the slope and deflections of the various points. Now, slope and deflections of various points. So, if if x equal to L by 2, if you substitute in this equation, slope comes, that is theta at a distance of L by 2. That equal to minus W by 2EI times 2L into L by 2 minus L square by 4. Now L by 2 get cancelled. L by 2 get cancelled. L square minus L square by 4. That is minus W by 2EI times 4 L square minus L square by 4. The final equation is obtained as minus W by 8EI times 3L square. That means 3 by 8 WL square by 8EI. That is x equal to L by 2. That is the slope value. And the units of the slope is radians. Units of the slope is radians. Is radians. This is the radians. Okay. Now, what about deflection? If you substitute x equal to L by 2 in this equation, the deflection at a distance of L by 2 comes, that is minus W by 6EI 3L L square by 4 minus L cube by 8. If you simplify this equation, minus W by 6 EI, now it is 8. That means that is 6 L cube minus L cube. That is finally at a distance of y at a distance of L by 2 comes as minus W by 6 EI times 5 L cube by 8. That means minus 5 W L cube by 48 EI. This is the value we can calculate. 5 L cube, 5 W L cube by 48 EI, where E is property of the material, that is the modulus of elasticity, and I, the value of the I is the second moment of inertia or moment of inertia. Now if you substitute x equal to 0, if you substitute x equal to 0 in this, then the deflection y equal to 0 and slope x equal to 0. What is the at 0 length? That means fixed support. The slope equal to 0. So at fixed support, what is 0? Y equal to 0 and theta equal to 0. At the free end, at point B, at point A, YA theta is 0. What about YB? That YB is minus W L cube by 3EI. What is theta B? That theta B is minus W L square by 2EI. So that means the maximum deflection of a cantilever beam is at the free end where the load is being acted. At the free end, the load acting, the deflection is there and the slope also there. The slope theta B and the deflection YB. These are the values for the span of L. Now, where W is the load, concentrated load, L meant for span of the beam, I modulus of elasticity, that is in Newton per square millimeter, and second moment of area is I, that is in millimeter per 4. So finally the units for deflection is in millimeters. The units of slope is in radians. Okay. Now this is what we calculated for a cantilever. We have calculated the slope and deflection of a cantilever beam. Alright. So it's very important for us. We use what type of method we use? We use it here, the double integration method. Double integration method. Is used for calculating the slope and deflections of a cantilever beam subjected to point load at free end. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.